Hei på. Hei, og velkommen til Artificial Summit nummer 9. I dag så har vi to foredragsholdere. Det er Malte, som skal snakke om reinforcement learning i Pac-Man. Og etterpå så skal Kristoffer snakke om hvordan du kan drive med bildegjenkjenning med Azures Custom Vision. Som alltid så har vi Creative Crew som streamer live. Og så disse videoene blir også lagt ut på YouTube etterpå, så ja, vær oppmerksom på det, og pass på hva dere sier. Ja, da er det bare å begynne.
Yes.
Vær så god.
Thank you. Okay, so I will do this in English as per usual. Are we ready for some Pac-Man? You're supposed to do woo! Okay. Yeah, so reinforcement learning with Pac-Man. Today we are going to start out by talking a little bit about reinforcement learning. We're going to introduce some terminology, and we're going to do some examples. Then we're going to continue on to Q-learning and do some examples from there as well. And then we're going to do a demo of Q-learning in Pac-Man. Then we're going to continue over to deep Q-learning and finish off with some demo of deep Q-learning with the Pac-Man agent. Yes, so reinforcement learning. In the last years, reinforcement learning has really become more and more hyped because of the results it has achieved, such as this one from 2013, which is DeepMind, who made an agent that plays Atari games, and it performed with the superhuman performance on several games. They also made AlphaZero, which plays chess, shogi, and Go, and also beat the world's best players in those games. And then OpenAI made OpenAI 5, which are Dota bots, and only 2 weeks ago they beat OG, which is the current world champion of Dota 2. And then DeepMind made StarCraft 2, or an agent that plays StarCraft 2. And I don't know if he beat the world's best players, but they beat really good players at least. So reinforcement learning is used a lot in games because they have some challenging environments. But the idea is to use the games as a stepping stone before going into real-world applications. So, and they're also used in real-world applications today, such as in self-driving cars, recommendation systems, in chemistry and medicine, and so on. Here's an example of reinforcement learning used in traffic light scheduling. So they put an agent in a complicated environment where traffic was represented as an 8-dimensional vector. And it tried to maximize the number of cars that gets through all of this traffic jam. And they got some pretty good results. Then I'm going to show a video. What do you guys see now? I need to switch this one. Okay. A video in robotics, it's also commonly used.
A variety of visual generalization
there is
experiments.
sound. Great.
The insets show the camera images that are fed to the policy. The hanger policy can handle different hangers and large objects that cover part of the view. The insertion task succeeds in the presence of new objects in the background, and can even insert the block when the cube is held in a person's hand. The hammer task can also be done with an arm in the scene, as can the bottle task. Here, the robot follows a moving target. The target did not move during training. When we cover the monocular camera,
That's it. No more of that. So we can see that reinforcement learning is also used in robotics, and it also achieves pretty good results. Let me change again. Cool. So a little bit of reinforcement learning theory. So you have kind of 5 terms that are really important to understand before you do reinforcement learning, and they're listed right here. An agent takes actions. For instance, it can be a drone making a delivery, or it can be Super Mario navigating in a video game. And in real life, you yourself is an agent, where you perform actions and you get some reward or punishment from society. An action is performed by an agent, where the agent has a kind of finite number of possible actions, and the agent chooses an action from this set. For instance, in Super Mario, he can run to the right, he can run to the left, he can jump, and he can duck down. The environment is the world where the agent moves. The environment takes the agent's current state and action as an input and returns an output of the agent's reward and its next state. So if you're the agent in real life, the environment is like the law of physics, for instance, and the rules of society that process your actions and determines the consequences of them. A state is a snapshot of the environment, and it is a concrete and immediate situation in which the agent finds itself. For example, it's a specific place and moment where the agent is put into relation to other significant things, such as tools, rewards, enemies, and so on. You can think about it as stopping time at any given point, and then you find yourself in a state. And all possible states then makes up the whole environment. The reward is a feedback by which we measure the success or failure of an agent's actions. For instance, in a video game, when Mario touches a coin, he gets some points, right? And here's how reinforcement learning works on the most basic level. If we start at the vertical striped line down to the left here, we can see that we have a state and a reward, which is the input to the agent. And based on this, the agent then performs an action in the environment. The environment returns the next state and the reward for that action that the agent performs. And then it continues like this in a loop until it stops. Let's look at a Super Mario state. So in Super Mario, the whole environment is the whole game, right? It's all possible states that the Super Mario can be in. The agent is Super Mario itself. The possible actions he can do, in the start at least, is run left, run right, jump, and duck down. And then you can shoot fireballs and something else, but we're not going to talk about that. Yes, so then Super Mario has to perform some kind of action. It has to choose, do you want to run left, right, down, or up? And when he chooses that, he's going to get to the next state. You guys see that? Yeah, boom. He chose to go to the right. So he goes to the right. The environment then gives you the next state, and it also gives you some kind of reward. Now here, nothing really happened, so there's probably not going to be a big reward in this step. If we look at another example of this robot here you have a new environment. It's the whole board kind of thing here. You have the rewards down at the bottom, and you have the agent, which is the robot in the bottom left corner. So here again, the robot chooses to make an action, and based on the rewards it gets, it should probably figure out that it wants to get to the exit point of this maze. Yes, so there is a couple of problems in reinforcement learning that you have to address. The first one is called the exploration versus exploitation. So let's say that the robot goes to the right the first time, and it gets a reward of 1, right? Because of the reward rules we have written down here. Now the next time the agent gets back to the initial state of this problem, if he just chooses to do the highest possible rewarding move, he's always now going to go to the right, because up is 0 because you haven't visited yet, but right, if you go right, you get a 1 reward. So it's always just going to go to the right. So that's why you have a small probability of an agent doing a random action. So after many iterations through this, the agent is eventually going to try to go up. And then it also sees, oh, I'm going to get a reward of 1 here as well. And now I have 2 equally good moves on the first state. And it's called exploration when you try new moves, and it's called exploitation when you do the move that is considered the best based on your agent. Another problem that you face when you're doing reinforcement learning is future rewards. So let's say that you're playing an RTS game or something, and you start the game and you're playing against an opponent, and you start the game and you have this building you can build, and if you build this building, it costs a lot of money up front, but it maybe generates more money as time progresses, right? And let's say you build this building in the start of the game, and then 15 minutes later you win the game because you have so much more gold than your opponent that you can just kill him, build warriors and kill him, right? And the agent might then think that it is what happened right before you won that made you win, but in reality, it is what happened at the very beginning of the game that made you win because you had so much gold. And this is also something you have to address when you're doing reinforcement learning. Okay, so let's talk a little bit about Q-learning. So Q-learning is an algorithm that learns how good an action is in a given state. And this value is called a Q value. So for each state action pair, there will be a score of how good these actions are. And when the model is trained, these Q values are a measurement of how good each action is in each game state. So when you run the algorithm, the agent simply picks the agents with the highest Q value for each state. You're doing the exploitation step. So let's look at an example here. If you have a game here where the agent is the smiley face, and then you want to get to the coin. So you set up some rewards. You give, for instance, okay, if you get the coin, you get 20 points. If you fall into a pit, you get minus 20. And then you introduce a move penalty as well. Because if you don't introduce a move penalty, the agent could go in a loop from state 0 to 1, 3, 2, and then back to 0 again. And then at some point, it can just jump from 3 up to 5 and grab the coin, and it can get the maximum amount of points. But you want the agent to go to the coin as fast as possible. So you introduce a move penalty, so it's just going to go straight to the coin. After the rewards are defined, you initialize your Q table, which is where you're going to store all your memory of your agent. And the Q table is a dictionary where each key to the dictionary is each possible state. So here we have 6 possible states. It's 0 to 5. And each of these states are then going to be keys to this dictionary. Then each state has a new dictionary, which are all the actions that are possible in each state. So it's kind of a nested dictionary. And the value of each action is the Q value. We're going to look at an example soon. First we have to introduce the update formula for Q-learning. It's this one. So you have the Q value to a state T and an action T. The way you calculate this is that you take the old value that you have calculated earlier, or if you initialized it, then it's 0. Then you take a parameter called the learning rate, and you multiply this by by the reward, which you get from the environment, plus a discount factor times the maximum Q value from the next state that is possible. And then you subtract the old value to normalize a little bit. We're going to look at an example right now. So let's say you have chosen a learning rate of 0.2 and a discount factor of 0.9. These are just like the normal go-to values. And you have your smiley face down to the left in the state 0. And let's say you chose a random action. You either go to 2 or you can go to 1, and you chose to go to 2. So then you plug in all these numbers in the equation, and you can see that since you got a reward, you get a reward of -1, But since your learning rate is 0.2, you have to take 0.2 times a -1, and everything else is 0 at this point. So you get a minus 0.2 Q value. And then you can update your dictionary accordingly. So here you can see that in state 0, if you pick action 2, the Q value of that is minus 0.2. And then you continue with this. And let's say you choose a random action again because you don't know anything, you just started. So you go to state 4, for instance, or tile 4. And you plug these values in again, and this time you get a minus 4 Q value. And you update accordingly. Now, state 4 is a terminal state, and when you enter a terminal state, you start the execution over again. And with this time, it's you have some Q values that you can use from. So if the agent now does some exploitation, it's going to go to state 1, right? Because state 1 has a 0 value, whilst if you go to tile 2, it has a minus 0.2. Or it can explore as well, and then it's just going to be random. And after a while, this kind of converges, hopefully, if you have implemented the update rule correctly. It's going to converge, and you're going to have a pretty accurate picture of this environment, and the smiley face is going to move up to the coin. So let's see how it is implemented in Python here. Here you can see. Is this? No. Okay. Can everyone see this? How do I zoom in? That is the question.
I think like command and then scroll.
Is the command? Oh, it is. That is correct. Okay, cool. Can everyone see better now? Yeah, cool. Okay, so by the way, this is a workshop that me and Manu and Eirik Folkstad made. We have held it once at NTNU. And Johannes, he made the game. That is correct. Yeah, there's no one else I forgot there? No. Okay. Okay, cool. So we're not going to look at any game code at all. We're just going to do the Q learning part of it. So here are the rewards for each move. I just say that if it captures a dot, you get 2. And if you get captured by ghost, you get a -5 reward, for instance. And these are just values that you just kind of figure out as you go. Nothing really, no empirical like evidence or anything is done here. I just plugged in some random numbers and tweaked them a little bit until it like kind of worked. And then you have, when you initialize the Q learning, you initialize the Q table, which is just an empty dictionary. Here's the pick action function, which has a probability of 20% to explore, to just choose a random move, or it has an 80% chance of choosing the most optimal move. We're just gonna skip these, blah blah blah. Okay, here's the training code. You initialize new game. Discount is 0.8 here actually, and the learning rate is 0.2. And then you loop through each episode. Remember, one episode is like one playthrough of a game. And here you can see on line 91, you pick the action, even if it's random or if it's the optimal one. You get the new game state, and you get an action event from the environment. And then if you won, you just print 1. And if you lost, then you check if you're in a terminal state. And if you're in a terminal state, the episode is done, and you start over again. You calculate the reward based on the action event you got from the environment. And then here's the update rule that updates the Q values in your Q table. Yeah, and then this is just a loop, and you choose how many episodes you run. This is also just try and failure parameters. Yes. So we can try. I have a pre-trained one, but we can train one later too. Okay, so when I start this one, it's not going to look like Pac-Man because this is custom made by Johannes Moskved. So the Pac-Man is going to be the agent that is in the bottom middle, and the ghost is going to be on the top in the middle. Just so we're going to run it multiple times, so hopefully everyone can see. I don't know how big it's going to be, but we'll find out. So here's the Pac-Man is the one that's dying, and there it won. I don't know if anyone really could see that. We're going to try again. So it's going to run around and take the coins, and when it wins, the game is just going to stop. I really didn't have time to fix that. So you can see the ghost is chasing Pac-Man, and there it won. Yeah. And it learns just by using the Q values. Oh, here's the same thing is going to happen again, and it's going to take. So this is a pretty small playing field. I'll try to run it again. They're lost. When you lose, you have 3 lives, by the way. If you can see to the bottom right corner, you have 3 lives. So you don't lose before the 3 lives are used. So it doesn't really care if it dies once, as long as it doesn't lose the game. So, and when it loses, you can see that they're just teleported back to the initial state. It's a little bit fast. And it had learned a couple of different strategies depending on how the ghost moves. I can see here. They're lost. Okay. Or they're lost alive. Okay, cool. Yes. Okay, so the problem with Q-learning is that you have this dictionary or your matrix of state action values. But if the number of all possible states gets too big, then having it in a dictionary doesn't scale at all. And therefore, you have to switch out the Q table with the neural network, because it can handle much larger state spaces. How it looks is kind of like this. It reminds you of the one I showed in the beginning a little bit. But we have the environment to the right, and then it returns the state and a reward, and then you plug it into a neural network, and then a neural network will tell you which action to choose. And then you take that action and you feed it back into the environment, and then it continues. But when you introduce a neural network, you have to do a couple of changes. So the input to a neural network has to be only numbers. So we have to somehow map the state to a vector with numbers. The other change is that you have to introduce, or you don't have to, but you should introduce experience replay, which I'm going to talk about a little bit later. So how you map it from a state to numbers is that we use one hot encoding. So, which is used when you have like categorical features in your data. So let's say, for instance, here if we have you have 3 colors. You have red, green, and blue, right? And how do you put these into a neural network? You can simply just say that red is 1. You can say like green is 2, and then blue is 3. But what you're telling the neural network then is that since we know 3 is bigger than 1, right? Everyone here can agree on that. So when you plug it in like this, you're telling the neural network that blue is bigger than red, which doesn't really make any sense, right? That's not what you want to tell it. So what you do instead is that you use one hot encoding. So you give a vector representation of each category. So red is going to become 1, 0, 0. blue is going to become 0, 1, 0, and green is going to become 0, 0, 1. So instead of a number, they're now represented as vectors. And you can see this is a text representation of the state down to the left here, the map you just saw, where the percentage signs are the walls, the G is the ghost, the P is Pac-Man, and the dots are the coins. And we do exactly the same as here as with the red, green, and blue examples, that we just check. We go through each tile of the state, and then we just have this super long vector that gets created. So instead of a state like text here, we just get a long sequence of 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, and so on. And this you can feed to the neural network. So one thing you can note then is that the size of the neural network input layer then depends on the size of your map, right? Because we're looping over the state. So let's say that the map is a 10 by 10 state, and each character get encoded to a one-hot vector of size 5, then you have an input layer size of 500, right? So it's going to change depending on how big the state for the Pac-Man game is. And the way you train it is going to be something like this. So you have a state, and then you pick the action, then you get the next game state and reward, just like usual, from the environment. And then you convert the state to numerical values, which you just did earlier with one-hot encoding, which you're going to get a long string of numbers, a long sequence of numbers. And then you're going to plug this into the neural network, which is just a black box for this demo here. And the target is then going to be a kind of a simplified function derived from the update value of Q-learning, which you can see here. It's a reward plus the discount factor and then the max of the next state. And when you're done training, what you're doing when you do inference is that you simply have the state, you convert it to values, you plug it into the neural network, and then it's going to give out an input, give out an output of all the Q values of each action. So it's going to, the highest value here is going to be the best action that you can perform with your agent. Yes, and then lastly, there's experience replay. So in Q-learning, when you just when your agent just plays the game, you simply just train it on a tuple of state action and the reward and the next state. But what we do here instead is that we save this to the memory, and then we train on random samples from it. So you train, and then it's going to be saved to some other memory, and then we draw random samples from this. The reason for this is that neural networks, like when you run your Pac-Man or your agent, it's going to start like increasing its performance, right? So it's going to kind of forget how it does the early part of the game, and it's going to get better at the late part of the game. So at some point, it's not going to be able to beat the early part of the game, and it's going to like train on that again, right? And it's just going to kind of not converge to anything nicely. So by drawing random samples from a memory, you're going to kind of distribute this. So it always trains a little bit on the early. It's going to train a little bit on the later game. And it's going to like train on the whole state space. It's also good because neural networks kind of need to see things multiple times. And when you have this memory, you just draw random samples from it. The same samples are going to get drawn, and you're going to train multiple times on it. So it increases the performance a little bit. Yes, so let's see on deep Q-learning. So I trained this for 25 hours and 55 minutes 2 or 3 days ago. What am I doing? I'm doing this again. So if you want to do with bigger maps, you have to use neural networks, because if you just use the dictionary, you won't be able to converge to anything. So here you can see again, these are almost the same rewards as I had last time. A little bit different. I don't remember why. I think they worked better, I guess. I didn't test this a lot. I only had one run. I only had one chance to train this agent. So you can see out here to the left, can you see that barely? I trained for 5,000 episodes, and I saved it every 500 episodes. So here you can kind of see the progress the Pac-Man did when you train. So we're going to run a couple of them. I only looked at the final one, which worked pretty well. And then you have the state to input conversion here, and the exploration. Oh, so the exploration here is not a set number anymore, because in the start you probably want to explore a little bit more, and then after you have trained for a while you want to exploit a little bit more. So you start with a high probability of exploring, and then you end up with a high probability of exploiting. Yes. The neural network I only trained, this is just using Keras, if anyone has used that. I only trained it on this architecture. There's probably a lot better architectures out there. I haven't tried it at all. It's a two-layer. Oh, there's two hidden layers, each with size 512 neurons, and then the output layer is the number of actions, right? So there's 4 actions in each state here. You can go left, right, up, down, and if you bump into a wall, just nothing happens. Yes. Okay, and it's very similar to the Q-learning. You choose an action, you get the next game state and a reward from the environment, and you check if you're in a terminal state. If you are, you start over. Here's the experience replay. So after you perform the move, then you add this experience to memory, and then you just draw a random sample from the experience replay. And we're just going to skip this. And then you train it on this, train it on the new experience that you drew from the memory. Yes, just train it. And let's try to run it. So this is the one I've tried before. I'm going to run that first because I know it kind of works, at least. So you can see a bigger map with 2 ghosts, and it's going to play. And when it hits those, I don't know what they are. Mushrooms. The mushrooms, okay. Then the ghosts get scary, and Pac-Man can eat the ghosts, and then he gets rewarded for that. So it's just going to run around, and something I noted is that it's going to kind of pick up the mushrooms in nice intervals so that the ghosts are scared the longest amount of time, right? Because if he picks up all the mushrooms in one go, they're just going to get scared for a small amount of time, right? But I think it has kind of learned to pick them up just as you go, so that the ghosts get scared. Yeah. So it's going to run, instead of taking those 3 coins there, it's going to run to the next mushroom so that the ghost continues to be scared, which is a funny thing. So they're going to get scared. They've been scared practically the whole time Pac-Man has played this game. Yes, Mane.
Isn't it because you probably have a higher reward
Yeah.
for the food?
Yeah, I have a higher reward for mushrooms, and there is a higher reward for catching the ghosts when they're scared. So yeah, it is a combination of those 2. So this is after 4,500 episodes. So the Pac-Man has played 4,500 games. It has either won or lost them. And yeah, so you can see it usually dies one time. There it died. But I think it is because it gets teleported closer to the missing coins than if he just had to walk there by himself. That is possible, or else he's just doesn't care about dying once, I guess. But yeah, so you can see when there's usually like some coins missing on the right side of the board, and then he runs to the left, and at some point on the left side he usually dies once, so he gets teleported back to the coins that are on the right side. He also doesn't have any more mushrooms to pick up. So here he dies, and then he just runs. So I don't know if he dies on purpose, but it may look like it. Cool. Okay, let's try to see like earlier in the training. I haven't tested these at all. Let's see after 500 iterations or episodes. Let's see. So this is early on in the training. I have no clue what's going to happen. Maybe it works perfectly now as well. Then I will be disappointed, but oh well. No!
That's pretty good.
Okay, well, I didn't need to run it for 25 hours then, I guess. Why didn't it kill the ghost? What is this? Okay, kill it.
Yeah, okay.
Okay, it has some problems.
No.
Move! Yeah, no mushrooms. It doesn't want to play if it doesn't have food. Oh, it died. Yeah. Oh, you lost. Oh, that's pretty cool. Okay, nice. Let's see a little bit longer out. Let's say 2,500.
You have to make dying hurt more.
Yeah, maybe. I think so too, because you don't want it to die, right? You want it to just try to not die even once. So if you make the punishment for dying greater, then maybe it won't die. Yeah. I think also a problem is there's a little bit too many mushrooms in this map. I don't know. The ghosts are just kind of running randomly away. Oh, it can't figure it out. Oh, but it has one on the left. Oh, it has one coin.
What to do?
What to do?
Surrounded.
Uh-oh.
If I hide long enough.
Oh, run down. Oh. Oh. Oh, I won. Nice. Okay. Well, yeah, as you can see, it's you can't really win in the start, and then it gets better and better as you train. Yeah, so that's pretty cool, I guess. Yeah. I think that's it for that. And then improvements for this. There's a ton of improvements. I trained this once using just random parameters on the neural network, for instance. You can just type in other parameters, and maybe it's going to be better or worse. Who knows? One thing you can do, though, is using convolutional layers. So this is just a normal feed-fork neural network. But what convolutional layers can give you is that they have kind of they perform really well in 2 dimensions. So when you see neural networks in images or pictures, it almost always at least, uses convolutional layers. Of course, more training time would be nice, more memory, more processing power. I don't think that's the case on such small maps that we saw now, really, maybe, because I got it kind of working a little bit. I think more tuning of parameters and stuff will improve more. There's also a thing you can do. Whoops. Haven't seen this one? Well, now you can see it. I'm on the 3rd point down here now. You can also add an additional neural network, which then stabilizes training a little bit more. And maybe you can get the same results with half the episodes that I've done. Instead of 5,000 episodes, you can maybe get the same results in 2,500. And then there's something called prioritized experience replay. So what I do is I draw replays or experiences randomly from the memory, right? But you can somehow give these experiences some priorities and be like, I want a higher percentage of the time get these experiences because they're more valuable right now, or something like that, right? Yeah. Yeah, and then a lot of parameter optimization. The rewards can be better, I'm sure. The neural network can be better, and yeah, all of these parameters are just pretty random right now. Yes. Okay, so that is it for me. You have any questions? No. Oh, did we have the Slido?
No, I forgot. Oh well.
Oh well. Oh well. I guess it's fine. Okay. Thank you, everyone. Thank you.
There you go,
Oh.
sir.
Oh wow.
It's for you.
Thank you.
5 minutter pause. Før siste. egentlig bare begynne.
Ja, men det blir litt mindre teknisk foredrag. Faktisk bruk av maskinlæring. Nå er det lyd. Tidligere år så hadde vi et hackathon hvor vi skulle redde miljøet. Og på bildet her så ser vi vinnerlaget, og til venstre så er det mitt lag. Så vi kom på andreplass, og det er selvfølgelig veldig stas det også. Og løsningen vi lagde var en app for å hjelpe Oslos borgere med kildesortering. Blant annet så kunne du ta bilde av søpla di, og da få beskjed om hvor det her skulle kastes. Og det klarte vi ganske bra. Den skilte på plast og glass, matavfall og forskjellige ting. Vi har en liten demo her, som ikke vil spille av. Det går bra. Det har vi planlagt for. Så her har vi da en webapp som tar bilde av en kanelbolle. Bildet blir lastet opp, og du får beskjed om at dette er matavfall, og det skal i grønn pose. Skal vi se. Ja, og det klarte mye forskjellig. Den klarte å gjenkjenne mennesker, tekstiler, glass og metall. Og i tillegg til å ha en app, så monterte vi også en Raspberry Pi med et kamera på en stabil ramme av papp og gaffateip. Og kunne da gjenkjenne om det du puttet oppi var matavfall eller ikke. Og med den informasjonen kunne styre en servo som åpnet opp luka og slapp det her ned i den grønne posen. Så hva må du kunne for å lage noe sånt? Ingenting, egentlig. Nesten. Microsoft har en del ferdige tjenester som vi kan ta i bruk for å gjøre det her. En av disse er Computer Vision, som er en ferdig trent datamodell, eller et API som du bare tar i bruk. Du laster opp bilder, og så får du en JSON-respons med hva som er på bildet. Dette fungerer jo veldig bra, men for vår del så er det ikke så interessant å vite om det vi tar bilde av er et skateboard, eller om det er en sko. For det vi ville vite var om dette skulle i papiravfall, restavfall eller matavfall. Så det vi tenkte er en egen måte... Oi, var det veldig dårlig lyd her? Er det fortsatt lyd? Ja. Vil du den ligge der? Ja, ok. Ja. Så vi er heller ikke interessert i å se hva som står på papiret vi skal kaste. Vi kunne vite at dette er papiravfall. Heldigvis så finnes også Custom Vision, der vi kan lage egendefinert bildeklassifisering uten å skrive kode. Så vi kan lage våre egne kategorier, men vi må da laste opp egen data og trene modellene selv. Det vi trenger som en minimum er 5 bilder innenfor hver kategori, og minimum 2 kategorier. Det vi får ut er et ferdig web-API som vi bare kan ta i bruk med en gang. Og det er veldig enkelt. Og da tenkte jeg vi skulle prøve å lage en app nå. Er det noen som ser på Silicon Valley? Kjenner dere kanskje han her? Jin Yang? Han lagde en app som heter Seafood, som da alle trodde var en app som skulle være The Shazam for food. Så hvis du satt på en restaurant og lurte på hva du hadde på tallerken foran deg, så kunne du da ta opp mobilen, ta bilde av det, og så fikk du beskjed om at det var et eller annet. Men så viser det seg at det eneste han har lagd er en app som gjenkjenner om noe er en pølse eller ikke. Og det er gøy, og også veldig nyttig, så vi kan prøve å lage det. Så hva trenger vi? Det vi trenger er 5 bilder av pølser, 5 bilder av ting som ikke er pølse, et Azure-abonnement. Så trenger vi en app som kan ta et bilde av en gjenstand og laste det her opp til API-et, sånn at vi kan bruke modellen vår til å fortelle hva det er for noe. Det regner vi med tar ca. 20 minutter. Så her har jeg et tomt prosjekt i Xamarin Forms. Det eneste jeg har gjort med det her er å legge inn en plugin for å hjelpe meg med å ta bilder, og så har jeg installert Newtonsoft JSON for å hjelpe meg å tolke responsen. Den kjører her, helt tom. Så for å ta bildet så trenger vi en image tag for å vise bildet vi har tatt. Image control, gi den et navn. Og under den så lager vi en button for å starte med å ta bildet. Tekst. Så legger vi på et klikk-event, så noe skjer når vi trykker på knappen. Skal vi se. Så, for å ta bildet så bruker jeg en plugin som heter Cross Media. Sync. Så vi initialiserer den, sånn at vi kan ta bildet. Og så take photo async. Og den telefonen her tar litt store bilder, så API-et nekter å godta alt for store bilder, så vi må komprimere det litt. Så vi sender med options og sier at vi skal ha compression quality er lik 50%. Og det vi får ut er en fil. Og den filen kan vi bruke som kilde til bildet vårt. File.path. Og nå skal vi ha en app som kan ta et bilde. Mens det bygger, så kan vi se på denne modellen vår. Her har jeg gått inn på customvision.ai. Her har jeg noen prosjekter fra før. Litt mat og litt søppel. Så vi kan lage et nytt prosjekt. Vi kan kalle prosjektet for Seafood. Vi skal drive med klassifisering. Vi skal ha en ting på hvert bilde. Og her har vi noen domener som kan gi oss en liten kickstart. Så vi velger food. Vi ser vi har også sånne compact-kategorier her. Dette er hvis man skal eksportere modellen og kjøre den offline. Så det er også mulighet til å gjøre det. Vi trenger ikke sette opp et web-API. Da kan du eksportere til TensorFlow for eksempel. Her har vi prosjektet vårt. Så skal vi legge til noen bilder, og da har jeg googlet litt allerede. Jeg har 5 bilder som er minimum. Laster opp disse og sier at dette er hotdog. Sånn. Ferdig. Og så trenger vi 5 bilder som ikke er pølse. Her er det da litt forskjellig. Sko, Big Mac, toast. Og vi velger den negativ, siden det ikke passer til kategoriene våre. Da er vi egentlig ferdig. Vi trykker 3. Det tar noen få sekunder. Og så kan vi da teste modellen vår direkte i browseren. Nå ser det ut som den her er veldig nøyaktig, men det er fordi treningssettet vårt er så lite at den tror den er mye bedre enn den er. Så vi kan gjøre en quick test og se om vi har bygd noe bra. Så jeg har litt testdata her også. En pølse i brød. Den er da 99% sikker på at det er en pølse. Det vi ikke har vist ennå er for eksempel en pølse i lompe. Men den skjønner det, selv om den ikke er like sikker. Så kan vi prøve en liten curveball. Her er det en hund i et pølsekostyme. Det skjønner den også, det er ikke en pølse. Så ved hjelp av 10 bilder så har vi klart å lage et API for å gjenkjenne pølser med ganske høy treffsikkerhet. Det vi også ser er at de bildene vi laster opp for å teste, de havner i predictions her. Og vi kan gå inn og manuelt tagge disse også. for å forbedre modellen. Så vil da være veldig nyttig å tagge bilder som den er veldig usikker på. Og når vi har tagget flere bilder, så kan vi trene på nytt. Og det tar nesten ikke noe tid før vi har fått en ny modell. Også veldig nøyaktig. Så i treningssettet vi brukte for kildesorteringsappen, så hadde vi rundt 2600 bilder fordelt på 15 kategorier. Så det lå litt mer jobb bak det enn akkurat der. Når vi er fornøyd med modellen vår, så publiserer vi den. Og det vi får er en URL vi kan poste bildet til, en prediction key som er en slags secret, og content type som vi legger på. Så må vi da legge bildet i body. Så tilbake til appen vår. Så kan vi prøve å ta et bilde. Her er en flaske. Ok. Og vi får den opp. Ok. Så det neste vi må gjøre er å laste det her opp til API vårt for å få en respons på om det er en pølse eller ikke. Så legger vi til en label her for å få skrevet outputen. Og så har jeg jukset litt. Jeg har kode her for å poste bildet. Så vi sender inn fila. Det som skjer her er at vi kopierer over bildet til en byte array. Vi lager en HTTP-klient, så vi legger til header for content type, som vi legger med prediction keyen vår. Og så trenger vi en URL. Hvis dette blir vellykket, så formaterer vi JSON pent, sånn at vi kan lese det, og så skriver vi det ut til den debug-labelen. Wait. Det tar litt tid å kompilere, men det går relativt fort. Så vi tar et bilde av flaska vår. Bildet blir lastet opp i bakgrunnen, og så skal det dukke opp der. Så det vi får tilbake er en liste med predictions, og en sannsynlighet for at det er for eksempel negativt. Den er veldig sikker på at den flaska her ikke er en pølse, for eksempel. Så det vi kan gjøre er å ta det øverste resultatet, og sjekke om tagname er hotdog, og hvis det stemmer, så har vi tatt bilde av en pølse. Så jeg jukset litt til. Jeg har laget litt datamodeller her, sånn at vi kan parse JSON over til objekter. Så i stedet for å returnere string her, prediction response, den inneholder en liste med predictions i sortert rekkefølge. Så da kan vi ta first or default. Da returnerer vi innenfor her en prediction. Ikke, så returnerer vi 0. Så i debug label så skriver vi da ut hva det ble klassifisert som, litt mellomrom, og sannsynligheten. Så kan vi gjøre det litt penere i UI vårt. Vi lager en grid her, sånn at vi kan legge ting opp på hverandre. Så oppå bildet så lager vi en label. Så sentrerer vi teksten. Under labelen, vi kan droppe activity indicator, skal vi se. Så før vi laster opp bildet, så tilbakestiller vi innholdet i outputen. Tekst. Og når vi er ferdig, hvis resultatet er en hotdog, så skriver vi ut hotdog. Hvis ikke, not hot. Takk. Sånn. Vi kan gjøre teksten litt større også, sånn at skal vi se. Ok, vi prøver det. Sånn, så ser dere hva som skjer her. Så vi tar igjen bilde av vannflaska. Laster opp. Får beskjed om at dette ikke er en pølse. Men hvordan vet vi at det her fungerer hvis vi har en pølse? Jeg har vært på Narvesen og kjøpt en pølse. Så vi kan prøve med den. Det ser litt trist ut akkurat nå, ligger i sekken min en time. Vi laster opp. Det er hotdog. Ok, så det har en del begrensninger. Du kan maks laste opp og trene med 100 000 bilder og 500 tags. Men til den bruken her så holder det jo i massevis. Du kan enten gjøre det her som et web-API som du bruker, eller du kan eksportere modellen for å bruke den direkte på telefonen, på offline. Hvis du har lyst til å prøve selv, gå inn på customvision.ai. Det er gratis inntil 2 prosjekter med 5000 bilder. Hvis dere som er utviklere her, har jo helt sikkert et MSDM-abonnement. Og da kan dere også bruke av det til litt større prosjekter hvis dere trenger det. Så da har vi sett at du trenger ikke være en like badass utvikler som Jin Yang for å lage tjenester som bruker avansert bildeanalyse. Takk for meg.
Spørsmål?
Ingen spørsmål. Vil du prøve? Sikkert ikke godt.
Veldig bra. Veldig interessant. Vær så god.